Today, we're diving into ultrasound. It's this amazing technology that lets us literally see inside the human body using just sound. And you know what's so cool about it? The whole idea is basically borrowed straight from the animal kingdom. We're going to break down exactly how that works. So let's just start with this question, right? We all know that animals like dolphins and bats can navigate in total darkness using echolocation. It's incredible. But how on earth did we take that natural superpower and turn it into a medical tool that can see inside our own bodies? Well, that's what this is all about. And that really gets us to our first big idea here, seeing with sound. This is where Mother Nature's blueprint meets some really clever human engineering. I mean, when you put them side by side like this, the parallel is just wild. On the left, you have an animal. It sends out a sound, listens for the echoes bouncing back, and its brain just builds a map of what's out there. Now look at the right, medical ultrasound. It's pretty much the exact same thing. A device called a transducer sends out sound waves, it listens for how they bounce off our tissues, and then a computer pieces it all together to create an image. It's literally biosonar just pointed inward. Okay, so we send sound in, we get a picture out. It sounds simple enough, but what's the magic trick here? What is actually happening inside that machine that turns a simple echo into a detailed image? This is where it gets really, really cool. The secret sauce, the absolute heart of the whole thing, is something called the piezoelectric effect. So inside every ultrasound probe, there are these special little crystals. When you send an electric current to them, they vibrate and create sound waves. But here's the brilliant part. It works both ways. When the returning echoes hit those exact same crystals, the crystals generate an electric signal. It's this perfect two-way street for turning one kind of energy into another. And this slide just lays out that whole elegant cycle perfectly. You start with electricity going into the crystals. That creates the sound waves that go out into the body. Those waves bounce off everything, creating echoes that come back, and when those echoes hit the crystals, they turn that sound back into electrical signals. And from all that data, the machine builds the image you see on the screen. Electricity to sound, sound back to electricity, all happening thousands of times a second. It's just so elegant. But of course, just like any job, you need the right tool. And not all ultrasound probes, or transducers as they're called, are built the same. They're actually highly specialized for different things. And here are the two big ones you'll see most often. On the left, we've got the linear probe. You can see it has that flat, straight head. And over on the right is the curvilinear, or just the curved probe. And yeah, you guessed it, their shape gives us a massive clue about what they're for. So, this table really breaks down the crucial trade-off. The flat, linear probe uses a high frequency. Think of it like a macro lens on a camera. It gives you these incredibly sharp, high-resolution, rectangular pictures of things that are really close to the surface. So it's perfect for looking at a vein in your arm or a gland in your neck. The catch? It can't see very deep. And that's where the curvilinear probe comes in. It uses a lower frequency, which can penetrate way deeper, giving you this wide, fan-shaped view of big organs like your liver or kidneys. You lose a little bit of that pin-sharp detail, but you gain that critical depth. So the choice always boils down to one question. Do you need to see detail, or do you need to see deep? And then you get these brilliant innovations like this, the double-headed probe. You can pretty much think of it as the Swiss Army knife of ultrasound. It literally packs both types of probes into one device. So a doctor can just flip from the high-res linear side to the deep-view curve side with just the push of a button. It's all about maximum flexibility without having to switch out tools mid-exam. All right, so we've got the right tool. Now what can we actually see? And maybe just as important, what can't we see? Let's talk about the different ways we can look at things and the technology's built-in blind spots. Okay, so the standard setting, the one you probably picture in your head, is called B mode for brightness. That's your classic 2D black and white image. But ultrasound can also show us things in motion using something called Doppler mode. This is amazing for things like blood flow. It can show you not just that blood is flowing, but which direction it's going, either towards or away from the probe. But here's the catch. As powerful as all this is, ultrasound is not an all-seeing eye. It has some very specific weaknesses, and they're all based on the simple laws of physics. So what gets in the way? Well, the two biggest enemies of ultrasound are bone and air. Bone is just too dense. The sound waves hit it and pretty much stop, creating this dark acoustic shadow behind it where you can't see anything at all. Air is the exact opposite problem. The difference between our soft tissue and a pocket of air is so massive that the sound waves just bounce off of it, almost like light hitting a mirror. And that's why it can be so tricky to get a good look at air-filled places like our lungs or our bowels. All right, so after looking at how it works, the tools, the limitations, let's zoom out and just recap the true power of this technology. When you really put it all together, it's pretty mind-blowing. We took a basic principle from nature, a simple echo, and we engineered this tool that gives us a safe, real-time window into the human body. And that word, safe, is absolutely key. Because it's just sound waves, not radiation. You can use it over and over without any harm. It's why it's the gold standard for checking on pregnancies and for guiding thousands of procedures every single day. It's just an incredible, non-invasive tool. And all of that leaves us with this one last, really exciting thought. This whole amazing technology started by mimicking dolphins. So it just makes you wonder, what's next? What other incredible secrets are out there in the natural world, just waiting to inspire the next breakthrough that could change medicine forever?